Good morning, everyone. Thank you so much for attending the 2024 Nick Besley Award webinar. This is actually a re-recording because there was an error with the original presentation of this webinar. But we're very excited to have all of you here, and I very much look forward to discussing this award and introducing the 2024 awardee, Professor Kevin Carter-Fenk. So, first, we're going to start with sort of an introduction to Nick Besley himself, as well as sort of the award. So Professor Besley obtained his BSc in chemical physics from the University of Sussex in the UK in 1994, and he finished his PhD in theoretical chemistry in the University of Birmingham in 1997 in the group of Professor Nels. His postdoc was with Professor Jonathan Hurst at the Scripps Institute, and then he also did a postdoc with our own Professor Peter Gill at the University of Nottingham in the UK. In 2022, he was awarded an EPSRC Advanced Research Fellowship, and he began his independent scientific career at the University of Nottingham with a promotion to full professor in 2018. Nick and his group added powerful new functionality to the Q-Chem software over a period of about 2 decades, and their contributions led to Q-Chem becoming a leading package for the simulation of spectroscopy of core electrons. He also contributed to the development of new exchange correlation functionals, novel methods for computing electronic excited states, extensions of TDDFT to predict X-ray absorption spectra, and methods for calculating harmonic and anharmonic vibrational frequencies within a partial Hessian formalism. He was an absolutely phenomenal teacher and supervisor and a great collaborator who could work both with experimental scientists and also theoreticians, effortlessly bridging the gap between those two groups. On June 27th, 2021, Nick tragically passed away after a bicycle accident near his home in Nottingham, England. Everyone who knew him was shocked by his loss, and the Q-Chem board felt that it would be highly appropriate to create an award in his honor to be awarded every year to commemorate both Nick's life and also to celebrate the impact of his research, both for Q-Chem itself and then also for the broader community. So this award was established to recognize excellence in the development and application of new methods for computational spectroscopy in the Q-Chem Open Teamwork Community Project. So looking back, I want to commemorate the previous Besley Award winners, Diptarka Haidt last year, and then Florian Matz a year before that. And this year, we are very pleased to announce that the 2024 Besley Award winner is Kevin Carter-Fenk. The award committee says it is our great pleasure to announce that the 2024 Nick Besley Award is given to Dr. Kevin Carter-Fenk, University of California, Berkeley, now at UPitt, for their valuable contributions to the Q-Chem quantum chemistry package, especially for developments in TDDFT for X-ray spectroscopy and variationally stable delta SCF methods for simulating ionization. So we are very excited to have Kevin here, and we are absolutely delighted to be presenting them with this award today, both to commemorate the contributions that they've made to Q-Chem and also to commemorate the contributions that Professor Nick Besley made throughout his career as well. He will be presented with this award, so congratulations, Kevin. You'll be getting this in the mail in a little bit. And we're very excited to have you as part of our Q-Chem developer community, and we are grateful for the work that you have done and are continuing to do in Q-Chem, and we very much look forward to what you will do as you are launching your own independent academic career. So thank you to Kevin, and without any further ado, let me go ahead and hand this presentation over to them.
Okay, so thank you for the kind introduction. I am honored to be the recipient of this award, and I can think of no better way to honor Nick Besley's work than by talking about X-ray absorption spectroscopy within time-dependent density functional theory. So today I will be taking you through some background on X-ray absorption spectroscopy. And then we will talk about computational methods for calculating excited states. In particular, we'll focus in on TDDFT-based methods, and then we'll get into how they perform for core excitations in general. And then we'll get into talking about electron affinity TDDFT, which encompasses the work that I have been doing in the last 3 years at UC Berkeley in Martin Head Gordon's group during my postdoc. And then we'll get to applications of the EA-TDDFT methodology and talk about some pretty cool work that has been has been done and is in progress. So without further ado, X-ray absorption spectroscopy is a spectroscopy of core electrons. So you have some high energy photon of X-ray wavelength incident upon the system that is capable of generating resonant excitations from core level orbitals into valence unoccupied orbitals. And for the majority of this talk, we'll stick with talking about the K edge. This diagram goes over some of the common nomenclature for the various types of transitions that you'll find in X-ray absorption spectroscopy, but we'll be sticking to excitations out of the 1s orbital for the first section of the talk, and then at the very end, we'll talk about some work that we've been doing at the M23 edge. And so X-ray absorption spectroscopy is a very nice spectroscopic technique in the sense that it really ameliorates the spectral overlap problem, especially in the K edge, where you can see that the various K edge onsets of these 3 next door neighbor elements on the periodic table are separated by upwards of 100 electron volts. So it's pretty straightforward to know what it is that you're looking at with X-ray absorption spectroscopy. It's also label and probe free, which is nice for probing the native structure of systems without the aid of dyes or any sort of fluorophores that might change that structure. However, it does require high energy photon sources that you might find at a user facility like synchrotron light sources, or even actually high harmonic advances in high harmonic generation have allowed people to start building tabletop X-ray instruments, which are really at the cutting edge right now. And so X-ray absorption spectroscopy can be used for a wide variety of studies, some of which that we will be looking at today are hydration structure. So it's very sensitive to the nuclear geometry of the system. So it's been very useful in studying the local hydration structure of solvated chromophores, and we can look using transient X-ray absorption spectroscopy. We can look at the interplay between electronic and nuclear dynamics, and we'll be taking a look at photodissociation in particular later on. You can also imagine using this technique, and it has been used to study the structure of metalloenzyme active sites, where you have metal atoms situated in an active site of a protein that, of course, has a K-edge onset that is well separated from any of the sort of biological carbon, sulfur, nitrogen, oxygen atoms that you might otherwise find in the protein. So it's all of this. All of this is built upon technological advances that have really taken flight in the last decade or so. But in theory, in the calculation of these core to valence type excitations, these are really on the frontier. So in terms of the fact that it's difficult to model X-ray absorption spectroscopy with the same degree of accuracy and efficiency that we can with which we can model valence excitations. So with that, I'll start talking about how exactly we model excited states, and then I'll pose some big questions. So we're going to stick with methods that only encode single excitations. So we'll talk about configuration interaction singles or TDDFT on this slide. So step one in any excited state calculation is to optimize the ground state molecular orbitals. And we do this via self-consistent field procedures. It will become apparent later that this is really a choice. And so this choice also has profound implications on the results that we get from our excited state calculation that follows. So step two is to generate all of the singly excited states. We then we then build the Hamiltonian in this basis of electron configurations, and we diagonalize it to obtain the spectrum. So the problem here is that the ground state molecular orbitals that we optimized in step one are not necessarily optimal for the excited states that we're trying to model, in particular when the charge distribution changes dramatically between the ground and excited states. And we'll find that applies to our the types of transitions that dominate X-ray spectroscopy. So now I want to pose the question as to which orbitals are optimal, and even taking that one step further to ask, what is electron correlation? So the textbook definition of electron correlation is everything that Hartree-Fock misses. So we have correlation energy defined by the true energy of our system minus some reference energy, or the energy of some generally the Hartree-Fock ground state. And so that difference is just the what we take to be the correlation energy. But if we are trying to model an excited state, for instance, what might happen if we choose a different reference, say explicitly optimizing an excited state electron configuration? So the true energy is not going to move anywhere of this state, but the reference energy will shift. And so the question is, can we find references that are better than the ground state reference, in the sense that can we find references that make this the correlation energy small in comparison to the Hartree-Fock ground state reference? Now, this is the fundamental idea behind delta SCF methods or orbital optimized DFT, and it will be important to later on as we discuss electron affinity TDDFT, but basically, if we can find reference orbitals where this is true, have we not baked into our initial reference what we otherwise may have ascribed to electron correlation? So that is the general concept that I want to explore in the rest of this talk. So now on to how we generally calculate excited states in quantum chemistry. Time-dependent density functional theory is really the workhorse of quantum chemistry calculations for valence excitations, and it really earns that title because, as you can see here, the errors with respect to theoretical best estimates across a variety of different functionals are less than half of an electron volt, and at the same time, TDDFT is computationally efficient enough that you can do a lot of calculations, TDDFT calculations on a desktop computer. However, as we dig into the core to valence transitions, the errors in TDDFT skyrocket. And the second thing that I'd like to highlight is that we also lose this this concept of Jacob's ladder, in the sense that as we build in more information about the density and the sort of Taylor expansion of the density, going from local information to gradient information, and so on, we hope to find better results, but that trend is broken here. And so why then does TDDFT struggle with core excitations? Well, the problems are twofold. So one problem is that TDDFT does not encode much orbital relaxation at all upon excitation. And what that means is that these orbitals that we have optimized and input into our TDDFT calculation, the ground state molecular orbitals, are not going to change much in response to changing the charge distribution. And so in X-ray absorption spectroscopy, that's particularly problematic if we can think of K-edge spectroscopy, where we are removing a 1s electron and placing it into a valence virtual orbital. We're basically changing Z effective by 1. And so from the ground state reference orbitals, we should expect a great deal of polarization that is imparted upon our orbitals by the change in nuclear screening. And so the second problem in TDDFT is really this idea of electron-hole self-interaction error, which is a byproduct of the fact that the exchange correlation functional is approximated in DFT. So what it looks like, however, is incorrect particle-hole interactions. So in pure Hartree-Fock theory, we have exact exchange, so we have an exact particle-hole attraction. But in pure density functional theory, there is no particle-hole attraction. So there is just this spurious interaction between the excited electron and the orbital it left behind, as if it were still there. So we have this error tends to dominate in X-ray absorption spectroscopy and leads to a systematic underestimation of excitation energies. So what I worked on as a postdoc, this electron affinity TDDFT, is really a formulation for time-dependent density functional theory from a core ionized reference state. And this is really reminiscent of the static exchange approximation from wave function theory, or otherwise known as electron affinity CI singles. But the fundamental idea here is that if we want to generate these core excitations, and we know that TDDFT supplies very little orbital relaxation, then if we change the reference density to something that looks more similar to the excited states that we're trying to model, say we bake in hole relaxation effects by self-consistently optimizing a density with a core hole in it, then we may shift our starting point to be closer to the excited states that we're trying to model, and thereby baking in orbital relaxation effects from the beginning. And so how might we do this? So step one is to optimize core ionized density. So we remove an electron from the core orbital that we want to generate excitations from. And to stabilize this core hole, we need to use non-Aufbau root homing methods like the maximum overlap method, or square gradient minimization, or state targeted energy projection. All of these algorithms that are available in Q-Chem really help to stabilize this. But so what we do here is we express this determinant with an additional spin orbital. So we have phi naught being the usual determinant that you might write out for this core ionized density matrix with a core electron missing, and then we add this continuum function. And so this doesn't explicitly enter the basis in these calculations, but it you'll see that it's a useful mathematical tool for formulating this formalism. So this continuum function is just a ultra diffuse orbital that doesn't interact with our system. So excitations into it from our system look like ionization, and excitations out of it into our system look like electron attachment. And so we make use of this, and you'll see that all terms associated with this orbital go away naturally, so we never have to include it in our calculation. Step two is to reattach this missing electron so that we regenerate our n electron density via linear response, because we are interested in the excitation spectrum of the neutral system, but we wanted to bake in that orbital relaxation with the core ion density. So what that looks like is regenerating this n electron determinant. You can see the excitations come from the continuum orbital and into our core hole. And so what that looks like mathematically is like a Koopman's electron affinity. And so you'll note the lack of two electron terms here. That means we're not encoding any orbital rotations, which is great because we don't want to change the orbitals that we have worked so hard to optimize with this core hole present. So the next problem we have to contend with is the fact that now that we have our n electron system back, we're going to do a second linear response, which excites that core electron into the virtual space. But in so doing, we'll reintroduce the electron hole self-interaction into the problem. And the real key insight that made this work was that we could, you can write the time-dependent response of the density and the corresponding Fock matrix in terms of a stationary component, and then you can factor out to first order different contributions to the time-dependent oscillations of the density, one of interest being the response to the electric field, another being the fact that we're starting with an n-electron density that is built out of the core ion orbitals, and so it's not a stationary solution. So there are some oscillations from non-stationarity. These, in fact, are not naturally included in any sort of TDDFT code that respects the Brillouin's theorem. And so we don't actually have to do anything to get rid of those terms as long as we don't include them in the first place. And then there's this contribution from self-interaction error that will change how the density oscillates. And so to first order, we can remove this self-interaction error exactly by abiding by this condition that we found, which is basically the left-hand side is the n-electron linear response within the Tamm-Denkoff approximation and that just looks like your usual TDDFT equation, except all of these n-electron quantities have been constructed out of the core ion orbitals. And then on the right, we have something that looks more like the static exchange A matrix. And if the left-hand side does not equal the right-hand side, then we have some residual self-interaction error, and that takes this form. And you can show that if you use the Hartree-Fock functional, this whole thing is the zero matrix, because Hartree-Fock has exact exchange and therefore no electron-hole self-interaction. And so finally, our electron affinity A matrix takes this form where we have Koopman's electron affinity step plus a self-interaction corrected linear response for the core to valence excitations. And so this is an exact self-interaction correction to first order, and therefore it's exact within the linear response formalism of TDDFT. And so we can write the full RPA equations for this, and they take on a really nice form that's reminiscent of electron affinity CI singles, or otherwise known as the static exchange approximation, where the first three terms are effectively the same, though with cone-sham orbitals in the DFT case. And then we get a correction from the exchange correlation kernel. And that's the usual sort of relationship that we often see between TDDFT and CI singles. And so just to recap and sort of show you how this works visually, what we do if we're interested in, say, the carbon 1s spectrum of benzene or the carbon K edge, we remove a 1s electron, and then we self-consistently optimize that density with the core hole present using some sort of root homing algorithm, and then we reattach the core electron via excitation out of this continuum orbital, and then we generate the exact n-electron excitations out of this single orbital, and their self-interaction corrected. So in principle, we've addressed both orbital relaxation and electron hole self-interaction problems that are present in TDDFT. And so in practice, let's take a look at how that works. So what we did was we benchmarked against 132 experimental K-edge XAS transitions that span the second and third periods on the periodic table. And these are examples of all the systems, small molecules and atoms that we included in this data set. It was basically everything that we could find in the experimental literature. And so one thing to notice right away is that EA-TDDFT recovers that Jacob's ladder concept that was lost before. So as we work our way up the rungs to functionals that include higher order information about the density, we generally see this decreasing trend in the errors. Up until at rung 4, we have errors at as low as half of an electron volt, which is quite good. And in comparison with TDDFT, the errors are reduced by at least an order of magnitude. And there is one notable exception here, and that is Nick Besley's own SRC1 functional that was parameterized specifically for K-edge XAS with TDDFT. And so there's a good reason that these errors are exactly the same. And so let's first talk about how sort of the best method / functional pairing compares across these three different approaches. So the TDDFT with Nick Besley's functional performs admirably in terms of TDDFT for X-ray absorption spectroscopy, but you can see that there is an increase in the errors as we go to period 3 elements. Electron affinity TDDFT maintains pretty much the same error margin between periods 2 and 3 on the periodic table. and in fact, overall performs similarly to orbital optimized DFT, which is fantastic because EA-TDDFT gives us a full spectrum in a one-shot calculation. All we have to do is optimize the core hole that we're interested in. And orbital optimized DFT, on the other hand, we have to explicitly optimize each electron configuration for each state. And now I want to show you the sort of insights that we can get from electron affinity TDDFT. Because we can isolate this the form of the electron hole self interaction error, we can separate it out from the relaxation error. And so that's what we've done here. In blue, we have the error from orbital relaxation. And in orange, we have the electron hole self interaction error, and then green shows the total. So Hartree-Fock theory is exactly what we would expect. There is no electron hole self interaction in Hartree-Fock theory or CI singles. We just have errors from the lack of orbital relaxation. And then for most density functionals, the electron hole self interaction error dominates, so we underestimate the excitation energies. But for Nick Besley's SRC1 functional, this really shows how far clever functional design and parameterization can get you, because it really the way it works is that it seems to leverage the fact that the orbital relaxation error points in the opposite direction to the electron hole self interaction error, and the parameters ensure that these two errors effectively cancel one another for an overall very low error. And so without explicitly including relaxation effects, the SRC1 functional is able to get really impressive results just by design, which is, and this is a very unique insight that we were able to get into how it works. And so now let's talk about some more physical systems in some of the projects that I had done as a postdoc, where we're looking at the NEXAFs of liquids and later aerosols. So we now have this method, EA-TDDFT, where we're able to isolate the impact of orbital relaxation effects on the X-ray absorption spectrum. And I was sort of inspired going into this project by work from Sonia Coriani's group, where they were using coupled cluster methods, both perturbative and iterative methods, CC2 versus CCSD, and they found that CC2 gave much less satisfactory results in these condensed phase applications in predicting the X-ray absorption spectrum, and they had hypothesized that perhaps it was orbital relaxation effects that are responsible. And so I was interested in sort of pinning this down. And so what we did was we looked at the oxygen K edge of liquid water and the nitrogen K edges of aqueous ammonia and ammonium. We generated structures through classical MD, and we took two hydration shells of explicit solvent molecules around our chromophore to account for short-range hydrogen bonding interactions. And then we embedded that within polarizable continuum model that accounts for the long-range electrostatics. Then we just contrast the TDDFT and CI singles results with electron affinity, their electron affinity counterparts. And so the results we get compared to the experimental spectra, which are all shown in black, the top row correspond to TDDFT and CI singles from the ground state reference. So your usual TDDFT and CI singles calculations seem to do pretty poorly, and they perform similarly badly as the CC2 results from Sonia Coriani's work. And in the bottom row, we have the electron affinity TDDFT and electron affinity CI singles results, which show dramatic improvements in the overall qualitative features in the spectrum. So at least to the point where we can now pretty confidently make assignments as to which peaks correspond to which transitions in the spectrum. And these methods are far more informative than the TDDFT and CI singles results that use the ground state reference density. So the big takeaway here is that orbital relaxation can be crucial for energies and intensities, which precludes this sort of idea that we can just compute a spectrum and then shift it around, which is a common correction applied to TDDFT calculations. So sometimes it is important to include this relaxation effect explicitly. And I will note that the CI singles calculations here serve as a sort of a litmus test for the importance of orbital relaxation, because we're not convoluting, we're not confounding the results with some sort of particular choice and density functional here. This is just comparing one method without relaxation effects to another that encodes them. And so this work is related to an ongoing project that I've been working on with Musa Ahmed at Lawrence Berkeley Lab, who's been looking at these glycerol aerosols. And so to sort of give the general motivation behind this work, though we're looking at a very fundamental aspect of this, but aerosol light interactions remain the largest errors in global climate models, in the sense that light from the sun hits clouds and either goes through or is reflected into space. And the particular structure at the molecular level of aerosols will impact how those particles interact with light. And so what we want to do is to inform some idea about what differences there may be in hydrogen bonding structure. And in our case, we're just using model systems of pure glycerol. And so these are NEXAFS spectra of that Musa collected of glycerol, the oxygen K edge of liquid glycerol at 298 Kelvin in brown, and then in black we have the oxygen K edge of glycerol aerosol. So these are collected at their instrument in situ, so they can actually observe these the X-ray absorption spectrum of the aerosols. But what they cannot do is easily assess the interior temperature of the aerosol. And so what you can see here are these subtle differences between the aerosol and the liquid. And so one of them being that the main edge part of this spectrum is much more broad, and then it leads into this post edge feature that is more intense across the entire this entire window that they were looking at. And so the hypothesis is that perhaps these aerosols, due to their high exposure of surface area to vacuum, may be evaporating very quickly, and in particular, evaporation is not barrierless, so you tend to lose molecules from the higher energy tail of the Boltzmann distribution first, and so the aerosols may be cooling down quite rapidly, whereas the liquid stays around 298 Kelvin. So that's the hypothesis, and that will influence the hydrogen bond structure. But Musa had no way of measuring this, so we sat down and decided, well, what if we apply this protocol with molecular simulation plus electron affinity TDDFT to pin down a ballpark estimate of what the temperature might look like. And so we did that, and we get qualitatively reasonable results, as we were getting before. And we get the right sort of idea in the post edge where the post edge intensity increases as we decrease the temperature. But one thing that was unsatisfying to me, and I think might be bothering some of you, is that all of these spectra so far have been pretty overstructured. And in particular, that overstructuring is evident here in the post edge, where we have a peak instead of a broad tail. And so I was digging through the literature and found this really nice work by Paisani and coworkers, where they were looking at the impact of quantum nuclear effects on simulated X-ray absorption spectra, and it seemed to look very much like our problem. So I took a shot at modeling the glycerol dynamics in a way that is inclusive of quantum nuclear effects. And so I used this adaptive quantum thermal bath methodology, which allows us to approximately account for quantum nuclear effects by thermalizing the 0 point energy. And so this is sort of a Langevin style thermostat with a colored noise contribution that accounts for this the harmonic 0 point energy. And so here we're just comparing the experimental data at 298 Kelvin with our simulated data from our classical trajectories. And this is the same spectra I showed you on the last slide. But then as when we add in the quantum nuclear effects, we get a much better spectrum. And so the pre-edge feature is much more sharp, and the post-edge is in much better quantitative agreement, and qualitatively it shows this really nice long tail. And so that suggests that electron affinity TDDFT is doing just fine in this system, but it needed better input structures because X-ray absorption spectroscopy is very sensitive to the nuclear configurations. It's very nice here to confirm that electron affinity TDDFT is sensitive enough to nuclear configuration that we can confidently say that quantum nuclear effects are responsible for the tail in the post edge of glycerol even at 300 Kelvin. And so quantum nuclear effects are important in glycerol due to the importance of hydrogen bonding overall in the structure. And so the summary of the liquid phase results is that we have good quantitative agreement with liquid phase spectra in EA-TDDFT relative to TDDFT. And so that allows us to learn a little bit more about these liquid phase NEXAFS spectra. And quantum nuclear effects are essential in the description of glycerol at 300 Kelvin and will definitely be important as we lower the temperature in our ongoing simulations. And so we are on the cusp of finishing those simulations. So keep an eye out for this. I think it's going to be really exciting work. And now I want to shift gears and talk about some work that we've been doing with Krupa Rameshesha's group at Sandia National Labs, where this was just accepted for publication in JAX. So this is the story of photodissociation in iron pentacarbonyl in gas phase probed at the iron M edge. So we're coupling transient XUV spectroscopy on the iron p orbitals to the iron 3p orbitals to our EA-TDDFT calculations to learn about the dynamics here. So the modern understanding of this sort of prototypical organometallic complex is that iron pentacarbonyl starts in its closed shell ground state. We then can excite it with 266 nanometer wavelength radiation, which is UV wavelength, into a metal to ligand charge transfer state. That's a bound state of the system, but then it quickly, through internal conversion, rattles down to these metal-centered states, which are dissociative, this process all takes place on the singlet manifold, as has been established by prior works. And so this happens very quickly, where the pentacarbonyl species loses a carbonyl ligand from the axial position first. And we're already in one of the two lowest energy singlet states. Still hasn't been evidence of anything happening in the triplet manifold, though iron tetracarbonyl and tricarbonyl have triplet ground states, so I'm sort of showing them here. And through more rapid internal conversion, we end up in the lowest energy singlet, and over the course of 3 picoseconds or so, we lose a second carbonyl, reaching our final product, which is iron tricarbonyl. And so we took a look at this process. First, we wanted to assess how EA-TDDFT performs on the static spectrum of iron pentacarbonyl. And so, and it turns out it performs beautifully. And so the EA-TDDFT results here are in the gray dashed line, and experiment is the black line. We're able to confidently then assign these lower energy transitions to 3p to pi star character, and some of the higher energy transitions start to populate the DZ squared. Now into the dynamics. So we lose an axial ligand first. So Banerjee and coworkers were kind enough to give us their non-adiabatic MD trajectories for this. And this is actually another method that's in Q-Chem. This is one-centered non-orthogonal CI singles approach, which is adjacent to electron affinity TDDFT, but Juan Arias Martinez is responsible for this approach that allows us to obtain spin pure spectra for open shell references. And so we can compare here. The top panel is the experimental result, and the middle panel is the theoretical transient absorption spectrum. And we can see good qualitative agreement. And in fact, this 65 EV narrowing of this 65 EV feature is due to electronic relaxation from the S3 and S4 states into the S1 and S2 states. So we're already in the lowest energy singlet states of these of the tetracarbonyl species by about 400 femtoseconds. So this happens very fast. And in fact, the electronic relaxation and this first carbonyl dissociation happen in concert. And so now we're going to look at static calculations, but calculations of candidate products, so unsaturated iron carbonyl species, just to get an idea about what might be contributing to which features in the transient spectra. So I'll note that some large active space CAS-SCF calculations that we did using Q-Chem's adaptive sampling CI code confirmed that the lowest energy singlet excited states of tetracarbonyl and tricarbonyl species are closed shell singlets. So we were able to just apply EA-TDDFT in its original closed shell form to these spectra. And what you're looking at in the top panel are these evolution-associated difference spectra that assume a sequential dissociation model. And at this first one, which is in cyan, is the time evolution of the spectrum in less than 120 femtoseconds. The second one in purple is everything up to about 3.3 picoseconds, and everything after 3 picoseconds is shown in magenta here. And so if we contrast that with electron affinity TDDFT from these lowest energy singlet states of tetra and tricarbonyl in two different candidate geometries, we see that we can reasonably explain some parts of the EAS signal. We can explain the rise in the signal as the formation of iron tetracarbonyl at short times and tricarbonyl at later times to this region between 50 and 60 electron volts, but we are missing a contribution at 53 electron volts. And so the question is, what's going on? And so what we did was we thought, well, maybe, just maybe, there is some relaxation into the ground state triplets of these tetra and tricarbonyl species. And so what we did was we implemented an unrestricted version of EA-TDDFT so that we can look at so that we can compute the spectra from the triplet reference. And I will just note in passing that we contrasted these results with EOM CCSD, and we get similar qualitative results, but EOM methods have size intensivity issues with their that would make them not as applicable here, but EA-TDDFT does not have that problem. So we stuck with the EA-TDDFT results, and we in fact get really nice results from EA-TDDFT that show a peak emerge that we can ascribe to this sharp rise in the sort of 53 electron volt region. And so the question we've posed then to the community with this JAX paper is, are there in fact triplets that are responsible for this feature at ultra-fast timescales? And we think so. We think that the combination of singlets and triplets here seems to rationalize the experiment the best. And I will note in passing that we did some additional EOM CCSD calculations that along this scissoring motion of iron tetracarbonyl, the 4-carbonyl intermediate species, between its two minimum energy geometries, C3V and C2V, which it spontaneously oscillates between in gas phase because of this very low energy barrier to get between those two geometries on that singlet surface. So the singlet surface does not just get close to the triplet surface, the triplet ground state of this system, but it in fact crosses in two places. And so even with some modest spin orbit coupling, there is precedent here for ultra-fast intersystem crossing, which is, I think, a fascinating result. And so in the end, EA-TDDFT corrects orbital relaxation approximately by building in whole relaxation effects by nature of the core ionized reference density that it uses, and then it corrects self-interaction exactly to first order to really improve upon TDDFT for XAS at very little additional cost. You're only on the hook for that additional core ion SCF, and the root mean squared errors are well worth it. And this new unrestricted EA-TDDFT implementation that allowed us to get at these triplet reference states for the iron species is coming soon to Q-Chem. And you can find the paper here very soon in JAX. So I would like to go over how you might run an EA-TDDFT calculation if you're interested. So the REM section is pretty standard stuff. Method, basis, choose your convergence criterion. Gnosis is the keyword that controls non-orthogonal CI singles, static exchange approximation, and the related EA-TDDFT approach. So setting that to true will trigger one of these options to be set. And then all of the options for EA-TDDFT are controlled in the $gnosis section. So EA-TDA is electron affinity TDDFT within the Tam-Dankoff approximation, which is the approximation that we adhered to for this whole talk. It's a very good approximation, but you can also request EA-RPA, which allows you to solve the full RPA-like expressions. And here you can also specify STEX or gnosis or one-centered gnosis. Here we set the number of reference orbitals. So in the glycerol example, we have, say, 3 oxygen atoms that we were interested in for the K edge. So we can set numref to 3 in that case. And then orb offset is the offset to that first reference orbital. So it's the number of orbitals that we're going to skip in ascending energy order. So for glycerol, again, we would set that to 0 for the oxygen K edge because the oxygen 1s orbitals are the first ones to show up. They're the lowest energy orbitals. But if we wanted the carbon K edge, we would set numref to 3 because there are 3 carbon atoms in glycerol, and we would set orb offset to 3 because there are 3 1s oxygen orbitals that we have to skip over to get to the first carbon 1s orbital. You can set the delta SCF algorithm, which can be set to IMOM or MOM, STEP, or even a marriage of the two, where the calculation will start with STEP for a number of iterations, and then it'll switch to MOM, which gives MOM a better initial guess. And that's been helpful in some cases. You can also set ref SCF algorithm to SGM if you want to use the square gradient minimization. With all of these approaches, we never have had any problems with optimizing that core ionized reference successfully. And so you can also change the convergence criteria for the SCF if you want, and choose to print singlets only or both singlets and triplets from a closed shell reference. And you can print the natural transition orbitals, which is very important for making orbital assignments. And if you do that, I will make the important note that you must set plots and make cube files to true if you're looking to print those. And so with that, I'd like to thank Professor Martin Head-Gordon at UC Berkeley for mentoring me as a postdoc over the last 3 years, and the rest of the Head-Gordon group. Special thanks go out to Musa Ahmed for collecting the glycerol NEXAFs data, both aerosol and liquid phase, for that project, and Krupa Ramashesha and Jan Tross for their experimental work with the transient spectroscopy of iron pentacarbonyl, and for EA-TDDFT methodology and code contributions. I'd like to thank Juan Arias Martinez, who is now a postdoc at Sandia National Labs, and Leo Cunha, who is a postdoc at the Flatiron Institute in New York. He's a Flatiron Fellow, which is very cool. I used Tinker HP for all of the classical molecular dynamics that I showed you, but of course used Q-Chem for all of the quantum mechanics, quantum chemistry calculations, and I'd like to thank the DOE and NIH for funding, and you for your time, and again, just I'm so honored to have received this award. So thank you.
Thank you so much, Kevin, for a fantastic talk. And we're I think going to not have a Q&A session now, but if anyone has questions, please feel free to post them on the forum. And thank you again to Kevin for giving such a phenomenal talk. We're really excited to have you as the awardee this year. And you've done a lot of phenomenal work, and I'm really excited to see what you'll continue to do as you start on your professorship. So yeah, congratulations.